Okay, so now let's go through these terms one by one, and I try to rearrange these terms and kind of give an intuition of what each of these terms mean. Okay, so let's first go through the first term. So first term, as you see, this is pressure, right? So these are pressure terms. So I can simply write that as u prime I. Let me rewrite that. Partial p prime over partial xk bar plus u prime k partial p prime over partial xi. Okay, so now I can use again that kind of relation in calculus for the derivative of multiplication. So it's going to be minus p prime partial u prime I over partial xk plus partial u prime k over partial xi bar plus partial over partial x j of p prime u prime I, and then I also add these canonical deltas, delta kj. So this is only valid when k equals to j. Okay, and then the next term is going to be plus, let me put these down here. I think that's better if I do this, write it down here, plus partial over partial xj of this term plus p prime u prime k bar delta ij. Okay, so this term is, we call this pressure diffusion term. And this term is called pressure strain rate term. Because we have strain rate there, and then we have also pressure. So it's kind of showing that, the combination of these two. Okay, so we can rewrite the first term as this. And now let me rewrite the second term here. The second term, so the second term is this term. So these second terms are, let's see, so the second term is kind of transport terms. And what I'm going to do, I'm going to add an additional term here, which is from continuity, we know it's 0, to rewrite this term. Okay, so let's do that here. So it's kind of 2 is transport terms or divergence terms. So the way I'm going to write this down is as follows. So I have this term, and then I'm going to add one additional term to this. So let me just write this term. So I'm going to add u prime I, u prime k, partial u prime j over partial xj. And what is this term? From continuity, we know it's 0, right? We already showed that partial u prime I over partial xi is 0. So if these indices are the same, so these are free indices, I can just change it to j. So partial u prime j over partial xj is equals to 0. So here, we know that, let me see, where is it? Yeah, here we know that this term is 0 from continuity. Okay, so this is going to be 0, and we add this at here as bar. Okay, and the reason I'm adding this, so it's just I'm adding a 0 to that, right? So it shouldn't, the answer should not differ. The reason is that, first of all, I want to write this as using again that formula for calculus for the derivative of multiplication. I want to write this as u prime I, partial u prime I, u prime j, u prime k over partial xj bar, right? We can do that. And again, we can take out this partial over partial xj, which is a derivative out of this averaging. So it's going to be u prime I, u prime j, u prime k bar. Okay. We know that this if you have let's say UVW bar, UVW d over dx, this is going to be UV dW dx plus UW dV dx plus VW du dx, right? So I just use this this thing from calculus and rewrote it in terms of this. Okay, so this is this term, and then let's go to the third term. So the third term, we have taus here. So it's kind of a dissipation. So these are dissipation terms because we have dissipation by molecular diffusion, tau. Okay, so let me see how we can rewrite these terms. So what I'm going to do here, I'm going to use the same technique for, again, these multiplications, the derivative of multiplications, but now I have two terms here. So I'm going to rewrite this similar to the first one, pretty much similar to the first term. So it's going to be equal to minus tau kj prime partial u prime I over partial xj bar plus tau ij prime partial u prime k over partial xj. Then I add the derivative of the multiplication, which is partial over partial xj of u prime I tau kj prime bar plus u prime k tau ij prime bar. Okay. So now I want to further investigate why this actually shows dissipation. So for a Newtonian fluid, we know that the stress is linearly dependent on the strain rate, right? For a strain rate, I can write strain rate Sij. I can define Sij as the strain rate of the flow is 1/2 of partial u prime I over partial xj plus partial u prime j over partial xi. Okay, so I can make this definition for the strain rate. And we know that the tau, or the stress, is linearly related to strain rate in a Newtonian fluid. Okay, so for the Newtonian fluid, we can rewrite 1 over rho of tau ij prime, let's say this term, partial u prime k over partial xj bar plus this term, tau kj prime partial u prime I over partial xj bar equals to, I can rewrite it as 2 nu times Sij, right? Instead of this, I can write as 2 nu Sij, right? So tau ij for a Newtonian fluid, we know it's 2 nu Sij. Okay, so I can just rewrite this. We know that these are linearly related, so I can write here 2 nu Sij partial u prime k over partial xj instead of the first term bar, and then for the second term I'm going to write skj partial u prime I over partial xj bar. Okay. So I can rewrite this for a Newtonian fluid in terms of the strain rates rather than the stress itself. So now we have these three terms that we kind of rearrange them. So now let's put that into the original equation. So rewrite this equation again. So let me rewrite that. So I want to rewrite that, and then we can discuss a little bit what do different terms mean here. So rewrite the equation. So if we rewrite that, so this is the first term remains as before, and then we have the new terms. So first is I'm going to add the pressure term here that we derived, right? So we have, it should be minus that here when we have it, and over rho, so we have to also divide it by rho. So we have, let me rewrite it here. It's going to be p prime over rho of this, and then we have the other terms. So let me rewrite them. Partial over partial xj. I can factor out partial over partial xj, and I have minus 1 rho. First, I write the pressure terms here. So we have p prime u prime k bar delta ij plus p prime u prime I bar delta kj. Okay. Then we have the transport term here, which is also has a partial over partial xj. So it's going to be u prime I, u prime k, u prime j bar. And then we have these strain stress terms here, which also have partial over partial xj. So I just need to write this down. These terms also have partial over partial xj. And instead of these terms, I can also write, instead of these terms, I can also write just their 2 nu Sij, right? So maybe let me write it down here. So we have partial over partial xj. This equals to partial over partial xj of 2, and I can also take 2 nu u prime k Sij bar plus u prime I Skj bar. Okay, so I can just write this down. And so let me write this here now. So we have plus 2 nu Sij u prime k u prime I Skj, right? So this is going to be also from the third term, which is the dissipation term. So these are all over partial xj. And then we have the terms that we didn't touch, which are these terms here. So this is the fourth term. So let me write this down. And I will go through what each of these terms mean. And finally, the only term that remains that I haven't written yet is this term. Right? And that term is we need to have a minus sign here based on what you see. So I add a minus sign of this minus 2 nu of this. So let me just double check. We have to minus 2 nu of Sij partial u prime k. Yes, and yes. So this is correct now. Okay. So Now let's see what are these terms and what each term here mean. Okay. So again, from what I said before, this term represents pressure. So we have pressure here. And then we also have strain rate. Strain rate. So this is pressure strain rate term. Okay. So what are these terms? These terms are all divergence, right? Because we have partial over partial xj. So these are all divergence terms. And they are also kind of the transport. So the transport, we also tell them transport, and I'm gonna come back. What does transport mean? But basically, it means that these terms just transport the Reynolds stresses from one location to another location. Okay. This term is actually what we call production term. So it's actually this is the production of turbulence or production of these Reynolds stresses. Okay. So these actually produce these terms. And this term, I'm going to come back, what do they mean? But this term is kind of clear. It's kind of the dissipation term. So it's actually the dissipation of these Reynolds stresses by molecular diffusion. New, right? So here, actually, these terms actually dissipates or destroys the turbulence or the Reynolds stresses. Okay. So again, this equation is called Reynolds. This is like the typical equation that we use and we show when we talk about Reynolds stress equations is this. So this is Reynolds stress equation. Okay. And these are different terms of that. Okay. So in the next lecture, I'm going to investigate this further, and I'm going to show that from this equation, we can actually get the turbulent kinetic energy budget equation, okay? But now I just want to make one note here and one remark here that, so why we tried to drive this equation. We tried to drive this equation because we had this closure problem. And we thought that, okay, if I can find, I have more 6 unknowns, which are more than the number of equations I have. So we thought if we can find an equation for this one, for these Reynolds stresses, we can actually close the problem, right? So we try to find additional equations so we can actually close these terms, these Reynolds stress terms that we don't actually know. So what we did is we started with the instantaneous velocity, and we decomposed it based on the Reynolds decomposition into a mean and fluctuating part. We had also the Rance equation, so we subtract Rance from the original equation, Navier-Stokes equation, and then we got an equation for fluctuations, which is written here. Okay, so this is what we did, and then in order to find the equation for the Reynolds stresses, we multiply this by U prime K, and then take the average here, and this is what we get. So this is actually an equation for the Reynolds stresses. So we kind of add these 3 and 4 together by changing the I and K, and we were able to get an equation for Reynolds stresses, which is shown here. Okay, and then by just rearranging the terms a little bit and defining these terms, we finally got to this equation, which is a more commonly used equation for Reynolds stresses. So now we have an equation that we can actually find these Reynolds stresses. This is kind of a transport equation for these Reynolds stresses. So we can actually integrate these in time and space and be able to find these Reynolds stresses at different locations. But here we face another issue. And the issue is Yes, we tried to find this equation, an equation for this, but now we have tons of new unknowns that has been added to our problem. Like, what are these? What are these pressure strain rate terms? How we can actually represent them in the flow, and how we can relate them to the mean flow variables. These are all different covariance and different fluctuating terms that are kind of multiplied by each other, and we have no clue what do they represent in the flow. So by trying to do that, we found an equation for Reynolds stress, but an equation for their Reynolds stress has produced many more unknowns. So we tried to find an equation for that, but then it actually led to more unknowns that we cannot actually find. So again, if we want to solve this, we need to parameterize these unknowns again. So this is kind of a loop that is never going to end. If we want to add more equations, we are going to get more unknowns. So this is actually the most difficult part of the turbulence problem, that we cannot close this, and this is called closure problem. Okay, so here, for example, we have added more than 75 unknowns. I'm not going to count them, but you can count them. Like P prime U prime has 3 unknowns: P prime U prime 1, P prime U prime 2, P prime U prime 3. So these are just three unknowns, and then you can look at all the unknowns. So we have actually added 75 more unknowns to the problem. Okay. So this is actually the difficulty of the turbulence problem, that we cannot actually close these Reynolds stresses. So we have to kind of model them, and these are all flow dependent. We will learn that they all depend on the type of the flow that we are investigating, and they can be really different in each flow. Okay. So in the next lecture, I'm going to further clarify these terms and find an equation for turbulent kinetic energy budget, which is very important piece of kind of concept in turbulence that kind of helps us to gain more insights about the turbulence and fluctuations in any flow. Okay, thank you very much, everyone.